We're going to explain a few things from Newton's laws of universal gravitation. It's early on a Tuesday morning and everybody's sleepy. We're going to watch a movie eventually, but I want to explain a few of these questions. We'll start with number 3. So look at your sheet, Newton's laws of universal gravitation, number 3. It says we've got a force. First of all, what's the law? What's the formula?
F equals G times mass over R squared.
Good. GMM over R squared. That's force of gravity. Now, number 3 says we have two identical masses. Yes? So I won't make a capital M and little m because they're the same mass. How about we make them two small m's?
M squared.
Good, Trev. Okay, so this becomes GM squared over R squared. You can only do this if they're the same masses. Okay, you can't do this if they're different. And now we want to find out what that mass is. So how are we going to solve for that M? What do I have to get rid of here?
So we want to do Fg times R squared divided by G.
How do I get rid of the R squared?
Multiply
I'm going to multiply by R squared. How do I get rid of the G?
divide.
Divide by G, right? And that's going to get rid of those things. But of course I have to do the same to the other side. And so we're going to end up with, I'll say Fg times R squared over big G. And that would equal M squared. How do I get rid of the square?
Square root of this.
Good. So I square root this. What else do I have to do?
Square root of the other side.
Good. So this is what I need, and once that happens, you can get rid of this square root and the square, and that will give you the mass. This is the hard part. This is the physics. The rest is just calculator work. Right? Now you just put in the force here, you put in the radius, square it, divide by big G. We all know what big G is, right? What's big G?
6.67 times 10 to the power.
Good. Does that number change?
No.
No. It's just the gravitational constant of the universe. So we plug that all in,
Different universe.
and we're going to get the mass.
In a different universe, we should be a different gravity.
One can assume. One can assume. And we actually don't know that the whole universe has that.
It's just an assumption.
It's an assumption. We haven't been very far, us humans,
So we could be
in space or time.
We barely even got involved.
It's possible that this is a total aside, so you don't need to know this. Just skip ahead.
Good.
Let's just say, I'll give you a scenario, possible scenario. Let's say that G does this. Starts here. Let's say that that is the value of G in the universe. And human beings have always measured it to be this, right? But what if we have only lived for that amount of time? And so we're just measuring the same G over this teeny little bit of curve. And we go, no, it's constant. It's always been constant. It'll always be constant. And then 10,000 years from now, it'll start dropping. And then our great grandkids who are like 5 million years from now, gravity will be reversed and they'll all be pushed away from everything matter. And we'll all be.
Does that actually theoretically happen?
No, we don't know. I just made this up. Don't.
Well, that's a good theory.
It's just possible, right? Same thing could be true with the speed of light. The speed of light may be changing over time. We haven't been watching long enough to know. We've only been writing stuff down for like 1,000 years. Seems like a long time to us, but compared to the age of the universe is 13.8 billion years old. So it's possible that amount has been changing the whole time. If the speed of light was changing, it would mean that time is going forwards, but will eventually slow down and stop and go backwards.
Now I.
No, that's one of the theories on how everything's going to law.
It's possible, yeah. We're on.
So, does mass always have to be in kilograms?
Yes, mass is in kilograms.
And then this, the R squared is in meters.
R squared is in meters, yeah. But the mass is a weird one because the SI units are always
Gram.
meters and, you know, joules, and there's no kilo or milli or micro. But for mass, for whatever reason, it was nice to have it in kilograms, so we kept it in kilograms. Do I have to do this math, or can you guys trust me on this?
Yes.
That's fine.
You need me to do the math? No? Okay. So you plug in your number. What's the answer we're on?
It's 186.
186 kilograms?
Yeah.
Okay, so for you at home watching this video, if you calculate this answer, you're good. If you don't, if you're putting it into your calculator and you're getting a different number, you got to figure that out with your calculator. If you can't figure it out, bring it to me and I'll show you how to do it on the calculator. Make sure you use the e's and not the times 10. Okay, that's number 3. That's the trick for number 3. I also wanted to do, I think it's 9, 10, and 11.
Yeah.
So flip it over on the back. What is the gravitational force on a 70 kilogram, that's a bad sentence. I forgot a word in there. What is the gravitational force on a 70 kilogram mass that is 6.38 times 10 to the 6 meters above the Earth's surface? There's Maria. Now there's a hard way to do this, or kind of the normal way to do this. Oh, you brought me Starbucks. Thank you so much. Where's mine?
I will.
If you're late, I told you this. If you're late, you have to bring
You
these.
gotta take a drink away now.
Yeah, I should. If this was pre-COVID, I would have just walked up there and taken that. Drank it. Good morning, Marina. You're on video now. Marina, if you take two masses, there is a force of gravity between them, yes? What happens if we double the distance between them? Yes, less. How much less?
Depends on the
Quarter
distance.
left?
I know, I gotta write this down. Take a look at the formula. This part in particular. What does the R stand for?
The radius.
Radius, or which means?
Distance.
Right. This is distance between the masses, right? This is an inverse square relationship.
That's all.
Say that with me. Inverse square relationship. So you flip it and square it. What is 2 squared? 2 squared is 4. Flip it over. What is 4 flipped over? 1 over 4. 1/4. If we double the distance, you will have 1/4 of the force.
So we're pretending GMM's not there.
No, this is all, it's all there. All this is still here. But if I double this, like let's say this is 1, right? We start with 1 meter. If I double it, what's my distance now? 2. What's 2 squared? 4. And so this is all of this divided by 4. So this force is now 1/4 of what it was. So if you have, let me write it for you. If you have R, you have Fg, right? Whatever the force is. If you have 2R, you have 1/4 Fg, because 2 squared is 4. Yes?
Sure.
Okay, what if, don't call it out. Put your hand up when the answer is in your head. What if I triple the distance? Then what is the force?
1/9.
So,
Sorry.
Okay, Thomas, tell us.
I think it's 1/9.
Levi, what do you think?
6.
Serena? Is it 1/6 or is it 1/9? What do we have to do here to get the 4?
Oh, it's squared.
Yeah. No, that's okay because in this example, 2 squared is 4, but 2 times 2 is also 4, right? So you did 3 times 2, which is okay. So 2 squared is 4. If we have 3r, what's that going to equal? 1/9 of the force of gravity. What if I go 4 times the distance? 1/16. You see where this is going, right? It drops really fast.
If you just do one, like what on the
What if I moved you, right now, how far are you from the center of the earth?
Pretty.
A fair amount. 6.38 times 10 to the 6, right? The radius of the earth. That's the distance we are from the earth's center, yes? What if I put you 10 times further out?
I would not be breathing.
What would the force of gravity be on you?
1/100.
Zero.
Good, good. Thomas, how did you get 1/100?
10 squared.
10 squared. So that's like a really, really small amount of gravity, right? So as you move away, the gravity doesn't go down linearly. It drops in an inverse square pattern, which is like a curve that goes like this. So you don't have to get that far away and then your gravity is really almost immeasurable.
They should make prisons inside of Earth.
They should make prisons inside of what?
Earth, like they just dig a deep hole and just go in.
They should make prisons inside of Earth. I really need to start writing these things down.
Dig a big hole.
Okay, so if I put you 6.38 times 10 to the 6 meters above the Earth's surface, what am I doing to the distance? Doubling it. Good, Arsha. So if I double the distance, what's the force of gravity?
2 times.
No, not 2 times.
4.
1/4, right? Double the distance, you get 1/4 of the gravity. So all you really had to do is take the force of gravity on the person, 70 times 9.8, and divide by 4.
But we can still do it that way.
Yeah, you can still do it this way too. But you'd have to take that radius and double it and put it in here. And you will find, it's kind of a good exercise, you will find it's the same. So take that force, whatever you calculate it out to be, and times it by 1/4, or divide by 4, which is the same thing. Does that make sense?
Yeah.
Do we need to look at the answer?
No.
No. It should be about, it was 70 kilos, right?
172.
So it would be around 700 normally, like on the surface. So 1/4 of that would be,
172.
yeah, 170 equals 1/4 of that, right? Okay. Number 10, what does number 10 say?
3 objects, each with a mass of 10 kilograms, are placed in a straight line 50 centimeters apart, so that's 0.5 meters.
Yeah.
And then what is the net gravitational force on the center object due to the others?
Is force a vector?
Yes.
Yes. Force is a vector. So does direction matter?
Yes.
Yeah.
Yes. So this guy in the middle, these are all the same mass, right?
Mm-hmm.
It doesn't matter what the mass is. The force of gravity this way is this much, and the force of gravity that way, is it different or the same magnitude?
Same.
The same, but opposite direction, right?
Yeah,
So-
so face the
If this is 10 and negative 10, what do they add to?
0.
0.
If it's 100 and negative 100, what do they add to? 0. So it's always going to add to 0. So the net force on this guy is equal to
0.
0. Nothing. Nada. No. Now, it's an interesting thing because with electromagnetism, you have repulsion as well as attraction, right? So if these two are repelling, the thing will sit there. Even if you poke it, it'll roll back to the middle. But if I just touch this, what's going to happen to it?
Touch what?
Like if these two are held in place and this one's free and I get it sitting right there so it's balanced, is it gonna stay there?
You might go wrong.
If nobody breathes and nothing touches it, it will stay there forever.
Yeah.
But if you just, what's gonna happen?
That'll go that way.
It'll go whack over here. Why?
Because it gets closer to that one for the force of gravity.
When it gets closer here, what happens to this force?
It gets more.
It grows. What happens to that force?
And then-
It shrinks. Not only does it shrink, but this shrinks more than this, or this grows more, and that shrinks more. It's not linear, right? This grows a lot, and that shrinks a lot. So it goes, and it's gonna whack into that thing. But if it's right in the middle and nobody touches it, net force 0, that thing will just sit there. It won't decelerate. Okay, so that's it. Okay, last one. What's number 11?
So 3 objects,
Yeah.
also placed 0.5 meters apart. on
Oh, I
the
could've left it
straight
there.
line. A and B have a mass of 10. B is in the middle, yeah. And then C is a mass of 15.
Ah.
What is the net force on B due to A and C?
Okay, so now we have two different forces, right? Which one is going to be bigger, right or left?
Right.
This is going to be bigger. Why?
Because C has a bigger mass.
This is bigger, so it's going to be a bigger force. And should we calculate it? Let's calculate it. So you're going to say, now, do you want to know the algebra bit for
Yeah.
this?
Yes.
So what you could do is you could say, okay, the net force is going to be these two forces added together, right? The force from, if this is A and this is B and this is C, the net force on B is equal to the force of gravity from A and the force of gravity from C. Yes? If you're real worldy, you won't write it like this. You're gonna say FGC minus FGA. Like this bigger force wins, so you're gonna subtract it. But if you're mathy, you say no. We always add the forces. This one just happens to be negative. You'll come to the same answer. Okay, if we do this, this FGA is big G MB times MA, right? Over R squared. This is still 0.5, did you say?
Oh, yeah.
0.5 meters, and this is 0.5 meters. Okay, and then we have to add, should we just make it negative to start with?
What do you mean?
Because one of the, this has to be negative because of the direction. So let's make that negative. And then we have to add the C one, which is going to be G, M, B, M, C. So just these two masses to find the force over R squared. Now the R squareds happen to be the same, right? So mathy people, what could I do with this?
Factor.
You can factor some out, right? So you could just say G M B over R squared, and what's left?
Hold on. MB.
This part is the same in both of these, right?
So MA plus, no, MA times MC,
And it has to be negative too, right?
negative MA minus positive MC. Oh, plus?
Yeah, plus. This is plus. So you could just do that if you wanted to. So let's calculate that. And that's going to be the net force on
B.
B, right? So we put in, it just makes a little bit less work, and you'll get faster at doing this kind of thing as you do more practice. But so we're going to put in 6.67 times 10 to the negative 11, and you're going to multiply that by the mass of B, which is that 10 kilograms?
Yeah.
Okay, thank you. divided by 0.5 squared. So that's 2.7 times 10 to the negative 9 here. Let's write that down. Just so you can follow along. And then we're going to add MC minus MA. That's just the way I would put it in. You can put in negative 10 plus 15. It's going to be 5 anyways, right? So this all adds to 5 kilos. So I have to multiply that by 5. And I get 1.33 times 10 to the negative 8.
Yes.
Is that the answer?
Yeah.
That's good. Okay. So very different this one. You got a lot of work to do because they're different masses, right? The point of that is that the force is a vector, so we have to take the direction into account. One of them has to be negative. So this one's going to move to the right, we all know that. But you can't just add the two values together because they're pulling in opposite directions. If you're going on in physics, to physics 12 and beyond maybe, you should be looking at this thinking, oh, there's a lot of troublesome problems in my future, right? How could I make this harder if I was like really mean?
We're not gonna tell you that. Why would we tell you
Marina,
that?
go.
The distances could be different.
Yeah, the distances could be different, so I wouldn't be able to factor this out. Okay, fine, yeah. What else could I do? You're not even really thinking.
You can add
Levi. Say that again.
Add words.
Add words?
Yeah.
You could add words to
Words
it.
and numbers are unholy.
That's fair, yeah.
Yeah, they speak.
I had a kid come to class one day and he had a t-shirt and it said, and on the 8th day, Satan put letters in math. I thought that was, we should get those shirts made. Justin.
Keeping the mass
No.
of the object below,
Say that again.
like hiding the masses of the object.
Hiding the masses of the object. Yeah, I could give you the distance. I could tell you that this moves
Oh my god.
0.1. It moves like 10 centimeters in 2.3 seconds. What is the mass of this? Then you'd have to use kinematics to find the acceleration of this. Then you have to use that to find the force on this, the net force. Then you have to subtract this force to get that force.
Actually, tension was better. Thank you.
Can we not put that on a dish?
If I was really mean, I would put angles in this.
Hell no.
So you would say, okay, you have a mass in the middle, but now this mass is not here. You would say, I would say, oh, you have a 10 kilogram mass that's 30 degrees down. Now what's the net force on this? How would you do it?
What is it?
You could use trig, right? How would you, this force would be in this direction, right?
Yeah.
This is all an aside, you're not gonna have to do this, but
Maybe.
at one point, some of you will have to do it. If this force is down here, how do I calculate the net force on this?
Do you
Levi?
do arrows coming off like every
Here?
single angle and then like match them?
Well, I wouldn't do every angle, but I would do vertical and horizontal, right?
Yeah.
So let me draw that bigger so that you can see it. So if you have your other, let's get rid of all this.
Oh, do you make it like a triangle?
Let's say I told you there was 100 kilos down here. You're gonna have this big force going down here, right? I would have to tell you the position of this guy. It's actually not that hard. You'd have to say, well, this is made up of a vertical component down and a horizontal component to the left.
And then you find the length of the.
Use your trig to get this and that. This one you add to the other horizontal. And then this is your vertical.
So it should be that hard.
It's actually not that hard, but you have to build a triangle at the end to get the final force. I'm not gonna give you that.
Yes.
Thank
But
you.
if you go on to physics 12, you'll have to do lots like that. So if you want to talk about it or practice or whatever, come to a next block. Let's watch a movie.
Thank you.